now I am absolutely delighted to introduce our first speaker. I would like to invite you to help me welcome Yann LeCun, Director of AI Research at Facebook, Professor at NYU, and founding father of convolutional neural nets. Yann has been a trailblazer for neural networks, and his work has inspired thousands around the world to take on machine learning. And his work has spurred breakthrough applications in diverse areas, ranging from image recognition to speech recognition to medicine and self-driving vehicles. Yann has been an amazing advocate for AI throughout the decades, throughout the ups and downs of the field, which is the hallmark of a true scholar. Yann has made many contributions, but I would like to highlight a project he did in 2003 as part of a DARPA seedling project to create a first proof of concept for an end-to-end machine learning system for autonomous driving. This project was called DAVE and really served as an impetus for today's NVIDIA approach to self-driving vehicles and to some of our own projects here at MIT. I have had the privilege of knowing Yann and his work for many years, and I am so impressed by his ability to be such a brilliant visionary while retaining his down-to-earth sense of humor and warmth. And so I was really not surprised recently when I learned that his name, LeCun, which derives from the old Breton form LeConf, means the nice guy. So we are so honored to have him today. Please join me in welcoming Yann.
Thank you, Daniela. It's a real pleasure to be here. I have to make a terrible confession. This is a conference about the future of work, and I'm certainly not an economist. But I hang out with a few economists, Eric among others, and I was at a conference in Toronto recently with a lot of very eminent economists who talked about AI and described it in terms of general purpose technology. So they see it as a technology that is going to diffuse across all of society and the economy and transform the way businesses in most sectors actually is done. And I never thought of it this way. I was really interested by the history of this in previous centuries of how this kind of technology percolates to society. So as I'm not an economist, I'm more going to talk about the science and the technology of AI and give a little bit of a state of the art, and then perhaps go on to talk about the limitations and how we could possibly go beyond the current limitations. So, you know, within, of course, you're all aware of the sort of history of AI. There has been, a number of waves of different approaches to AI, many of which had a lot of hope behind them, which were not necessarily fulfilled in the end. And when the hopes are not fulfilled, the wave of interest in this particular set of techniques kind of die down. There were several ways of machine learning and neural nets. There were several waves of more kind of symbolic approaches and other types of approaches. And right now we are pretty close to the peak of a new wave, perhaps started by the sort of deep learning, the emergence of deep learning. Every time that such a wave occurs, the set of techniques that are developed after a while kind of go underground and become part of the toolbox. And we don't talk about it in terms of AI anymore. So if you go to the old history of the first wave of neural nets, it looks like all work in that domain kind of stopped in the late 60s, partly because of a book written by MIT professors, Marvin Minsky and Seymour Papert. But in fact, it just changed name. People kept doing what they were doing, except they call this adaptive filters instead of machine learning or artificial intelligence or artificial brains. And you see this in the various waves of AI. And so I'm kind of wondering what's going to happen to this wave. What is it going to be called 10 years from now, 5 years from now? And what's going to be the next wave? So what we can do with AI now that we couldn't do before, or at least not to the same extent, is perception. And that has, of course, a lot of applications everywhere in the economy. So things like medical image analysis, and self-driving cars, which are probably the two most visible applications that will pop up over the next few years that the public will be aware of. There's a lot of other applications for accessibility, for the visually impaired, for example, translation, sort of connecting people, something that Facebook is really interested in, virtual assistants, although that's going to take a while. And of course, search, content, information retrieval, game, security, etc. And science. Science is actually being affected by deep learning as well. So all of those applications currently use supervised learning. And supervised learning is, I'm sure there are economists here in the room, it's like regression, right? You have inputs and you have outputs, you have x's and you have y's, and you have to kind of learn a function that maps x's to y's. And you have a limited number of samples, and you hope that with the limited number of samples that you have, the machine will be able to kind of learn a suitable mapping. So you want to, for example, map speech to words, images to categories, portraits to names, photos to caption, text to topics, things of that type. And so basically, the process is the machine is a function with lots of parameters on it that can be tuned, symbolized by those knobs here. And you show an image, or whatever input it is, you wait for the machine to produce an answer. If the answer is wrong, you tune all the parameters so that the output gets closer to the output you want. And that's supervised learning. That's quite successful, and I would say, I don't want to say a percentage like 95%, but pretty close to 100% of all applications of machine learning you see basically result from supervised learning. So the next question you might ask is, how do you build this box? And of course, it's not a physical box anymore, although it was in the 50s. It's a piece of software. And a particular way of building those boxes are things like convolutional nets or recurrent nets, or there's a whole menagerie now of particular types of architectures that are derived from recurrent nets or convolutional nets or other mechanisms and sort of assembled into blocks. And that's really the substance of deep learning, the fact that you can take functional blocks, each of which has parameters, tunable parameters, and you assemble them in some sort of compute graph. And if all of those modules are differentiable, you can use deep learning or gradient descent to train them. So there were early applications of neural nets, many applications, some relatively small scale, some larger scale. One the applications I was involved in is for character recognition, and those things were really widely deployed in the mid-90s for recognizing checks and various other documents. But that didn't stop the field from losing interest in those techniques in the mid-90s. And I think the sociologists of science will have to figure this one out, because I was too much in the thick of it to really kind of understand what the dynamics of it was. But it's interesting to kind of know why that happened, so that we perhaps figure out how to do it differently next time. So what happened over the last several years, last 5 years roughly, is that these ideas that go back to the 90s were brought to the fore because computers became more powerful, data sets became bigger, and those methods thrive on big data sets. So you need to have a large number of samples to train a neural net, a deep learning system, for a new task. Once the system is trained, if you want to add a category to what the system recognizes, you don't need that many samples, but the first pass of getting the system to learn anything, requires a lot of samples. And it's not until recently that our kind of digital world was kind of producing enough data for this to be possible, except for things like speech recognition and handwriting recognition. So what happened about 7 years ago or so is that data sets for image recognition became available that were big enough to train those systems, and the GPUs appeared, which allowed my colleague at University of Toronto, Jeffrey Hinton, and his students to implement very efficient convolutional nets on GPUs, and then beat records for image recognition that sort of helped change the mind of the computer vision community and later other communities towards those methods that were kind of skeptical before that. And since then, we've been seeing an inflation of the size and number of layers of those networks and the kind of menagerie of different architectures. That's what kind of makes it interesting. Daniela mentioned one of the robotics projects I was involved in. I should say, actually, the idea of learning a robotics task for driving end-to-end actually goes back to the 80s. It's not me, it's Dean Parmelo at CMU who trained a neural net, not a convolutional net, to drive a truck. It was somewhat successful. It's called Alvin. And what we did more recently was to use convolutional nets for that. And then after that, DARPA decided to fund a project for off-road robot driving that allowed us to develop those techniques based on convolutional nets to kind of label every piece in the image as to whether it's traversable or not. And it turns out you can drive robots this way. That worked pretty well. These are two of the students who work on this project. Raya Hetzel, who is here. She leads the robotics group at DeepMind, and Pierre Samanet, who is annoying this poor robot, who is working on robotics at Google Brain. They're pretty confident that the robot is not going to run them over because they actually wrote the code and they trained it. So, so this was kind of state of the art, maybe for convolutional nets for driving and image recognition, perhaps in around 2008. And what's happened since has been nothing less of astonishing for me, even for me. This is a very recent work. In fact, it was presented at the ICCV conference last week by a number of researchers from Facebook AI Research in Menlo Park. The lead author is Kai-Ming He. And it's a particular type of convolutional net called mask-RCNN. They combine several techniques. And what this system can do is do what's called instance segmentation. So it can take an image and then draw the mask or the outline and the bounding box of every individual object and then label them with a category. And it knows the individual object. So it doesn't label the whole blob here as person. It knows each individual person. And the performance of this is really impressive. In fact, this paper won the Best Paper Award at ICCV for that reason, and can pick out small objects in images, objects that overlap each other, etc. Pick out, backpacks, count sheep. There's always a sheep picture somehow in computer vision. And do various other things like this with partial view and occlusions. And if you would ask a computer vision researcher maybe 5 years ago or 10 years ago, how long is it going to take us to solve this problem to this extent, they probably would have refused to make any prognosis. This was very, this seemed completely unattainable a relatively small number of years ago. The same system can be trained for multiple tasks, so things like evaluating the pose of human bodies, and that's very useful for a lot of applications in augmented reality, virtual reality, but also knowing what people do in images and things like this. So this is perception. So perception really works, and there's a huge number of applications that this can be used to, medical imaging and self-driving cars being the first ones. But what's missing here, one thing that's missing from perception is reasoning. So intelligence is not just perception, right? There's also reasoning, there's memory, there is planning, there's all those things. It's common sense. Daniela mentioned that. Daniela mentioned two things in her talk, common sense and fake news. I'm going to talk about the first one, but not the second one. And here is an example of some work that addresses the problem of reasoning. So let's say you have a problem of this type. This is visual reasoning. This is also a paper presented at ICCV. The lead author is Justin Johnson, who was an intern at Facebook a couple of summers ago. And the problem here is to answer questions of the type, is there any matte cube that has the same size as the red metal object, for example? Things like that. Or perhaps a question of the type, are there more cubes than yellow things? Okay, so if you want the system to answer this question, it has to kind of configure itself to compute the answer. And what they figured they could do was feed the sentence coded in a sequence of vectors to a recurrent neural net, LSTM. That LSTM produces a vector that represents the question, and then feed it to another LSTM that basically regurgitates it in terms of a program, if you want, a visual program. And this program is going to produce a graph of operators that are meant to answer the question. And this graph is generated dynamically as a function of the question. So it's a bit of a, not such a new thing in neural nets, but something that is gaining popularity. Is the idea that the architecture of the neural net is not fixed, but it's data dependent. It's called dynamic graphs. And one of the things we've been working on at Facebook is write deep learning frameworks that can deal with dynamic graphs. It's very important for natural language understanding and for a number of applications, and for things like reasoning. And so what this system will do is produce this graph of operators. The first operator is going to filter the yellow objects, if you want. So it's going to produce a mask that has one blob for every yellow object. Another one that filters the cubes, another one that counts each of those objects, and then another one that compares the two, and then you get the answer. And the beauty of this is that you can basically train all of this with backprop. There is sort of a discretization step here somewhere, so you have to use so zeroth order optimization there. But there are newer versions by Aaron Corville, for example, at University of Montreal, that built up on this work since it appeared on arXiv, that are completely differentiable and very interesting. So this idea that you can sort of conflate reasoning or allow deep learning system to reason, not just to kind of perceive, I think is something that's very interesting in terms of research avenues. So there's a number of issues with supervised machine learning, and some of them were mentioned by Daniela before. Machine learning reflects, supervised learning reflects biases in the data, and that might have very dire societal consequences if that problem is not dealt with in appropriate ways. If the data is generated by people and the people are biased, then the machine will just reflect these biases and perhaps even amplify them. So there's a number of work on trying to reduce those biases systematically in data. So have machines that are less biased than people. I'm personally really very optimistic on that account, in the sense that I think it's going to be easier to remove bias from machines than it ever was from people. And at least we can have methods that to some extent could do this. There are other questions. How do you test for reliability? Well, the system is not, we can't use formal methods as sort of in traditional computer science. When you write an autopilot for an airplane, you can write the program in 3 different ways and then run verification systems on it. Here you train the machine, and so it's going to make some mistakes, and the reason and the question is how much. There's a question that's discussed a lot, which is whether decisions made by AI systems should be explainable. So my position on this is that it's not as useful as most people think. The vast majority of decisions made by machine learning systems don't require explanations, and in fact, there would be no one to really look at those explanations. So I think it's not as useful as people think, but there are certain decisions when they concern people or when the decisions are inputs to human decisions where explanations are very useful, like in the legal domain, for example. And there's been a bit of a myth that neural nets are black boxes, that we can't really understand what works inside. That's not true. I mean, we can. It's a program. We can look at all the variables. We can do sensitivity analysis. There's all kinds of techniques for this. The reason they're not used is because they're not that useful, at least in the use cases that we have today. So let me switch gear and talk about the limitations of those methods and of supervised learning, and then talk about how we could sort of go beyond that. So there are really 3 sort of modalities of learning, or paradigms, if you want, in the machine learning context. One is reinforcement learning. There's supervised learning and unsupervised learning. So supervised learning, we already saw what this is. You tell the machine what the correct answer is, and you give it a significant amount of information every time it goes through a trial. You tell it the right answer, so it's a fairly large number of bits you give it. Reinforcement learning is the process by which you don't tell the machine the correct answer, but you tell it whether it did good or bad. You basically give it just a single scalar once in a while. And the machine has to kind of figure out by exploration what output would have maximized the score. So the feedback is much weaker. And the result is that the number of samples that are required for the machine to learn anything is much, much larger than in supervised learning. And then there is something called unsupervised learning, or perhaps I prefer the term predictive learning, which would be a mode where the machine basically learns how the world works by observation, just looking at the world, kind of like babies and animals do. So let me talk a little bit about reinforcement learning. So it's kind of brought to the attention of people for various things. Machines that can play games, they can basically train themselves to play games by just trying to maximize the score. And for simple games, or games that are simple to simulate, thousands of frames per second, like Doom or Go or things like that, the machine can play millions of games in a relatively short time, perhaps in parallel on multiple machines. So it works because there you're not limited by the number of trials. In games, you can run games so fast and on so many machines that the machine can learn fairly quickly. But it doesn't quite work in the real world, because if you want to use reinforcement learning to drive a car, the car will have to drive off a cliff about 50,000 times before it figures out it's a bad idea. And so you can't do this, right? So what people try to do is basically use simulators and then try to transfer the skills learned through simulation to the real world. Or perhaps find other ways, like we seem to be able to learn to drive without crashing too many times. So how is it that we can do this? Right? What kind of learning are we using? So that's really a question that has been bugging me for quite a long time. That led me to this slightly obnoxious analogy, or at least obnoxious if you are kind of a true believer in sort of pure reinforcement learning, which is if you measure in terms of the amount of information you give to a machine, or you ask it to predict for the different modes of learning, and you think of intelligence as a cake. Being a Frenchman, I kind of have to do that. But actually, it's a Black Forest cake. It's more like a German cake. So the bulk of the cake would be, in terms of amount of information you ask the machine to predict, would be unsupervised or predictive learning. The icing on the cake would be supervised learning, and the cherry on the cake would be reinforcement learning. Now, this is a Black Forest cake, and the cherry is not optional. So you need your cherry. I mean, you need to kind of drive the system to sort of learn things that are useful for a task. So this is not saying that reinforcement learning is useless. This is saying that it's not sufficient. Supervised and reinforcement learning are not sufficient for learning complex things. So how could machines learn like humans and animals? By essentially observing the world. And this is really the question of, can machines acquire common sense? And I think of common sense in very general terms. So I think a cat has common sense, some level of common sense that machines don't have. Cats can understand the dynamics of their body and various things much, much better than any learning models that we have. So in my mind, and this is a very personal opinion that not everybody agrees with, is common sense is the ability to fill in the blanks. So you have partial information about the state of the world through perception. And common sense allows us to kind of fill in the blanks because we have background knowledge. It allows us to fill in the blanks. So if if you only see my left profile, you can tell what my right profile roughly looks like, because most human faces are more or less symmetric. You have a blind spot in your retina, but your brain kind of fills it in. And you don't even realize you have a blind spot. You naturally predict the future. You have some idea of the consequences of your actions. You have some idea of what's going to happen in any situation that you encounter. So the ability to predict, to some extent, is the essence of intelligence, really. The ability to form models of the world. Hopefully, causal models. And what we need to get machines to kind of learn how the world works and build models of the world is this idea of predictive or unsupervised learning. So babies do this. Babies learn things like object permanence or gravity, intuitive physics. Big apes do this. This is a baby orangutan that is being shown a magic trick at the bottom here. where the object inside the cup is removed without his knowledge. Then he looks at the empty cup and rolls on the floor laughing. Because it kind of breaks his model of the world. And this is a young orangutan. In fact, people do experiments like this with babies to figure out at what age they learn those basic concepts about the world. Is the world three-dimensional? How do we learn to track faces? That, how do we learn that an object that is not supported is going to fall? Things like that. And so a colleague in Paris, Emmanuel Dupoux, is a cognitive scientist at École Normale Supérieure, established this chart here, which indicates at what age babies learn very basic concepts. So things like gravity and inertia, conservation of momentum, so basic intuitive physics, babies learn this around the age of 8 months or so. It's not something we're born with. It takes a while to kind of figure this out. Before 8 months, if you show something like what's shown at the upper left, where a little cart is basically suspended in the air, before 8 months, babies say, well, that's the way the world works, fine. After 8 months, they react like the little girl here at the bottom left. They open their mouth like the monkey, and they open their eyes, and they fixate, and they say, what's going on? They don't say what's going on, they think what's going on. So we could ask the question, how do we get machines to do this? And first, we have to think about the architecture of a complete AI system. So it has to have, it produces actions that act on the world responds through percepts that give, a partial view of the world. And inside the machine, there is an agent that feeds its state to some sort of objective, and the objective kind of measures how happy or unhappy the agent is, essentially. We have something like this at the base of our brain. It's called the basal ganglia, and it basically tells us if we're happy or not. It tells us if we're in pain, if we're hungry. It computes all those things. And what you would like to put inside of the agent is something that contains a model of the world that allows the system to sort of predict what's going to happen in the world, just because the world is being the world, or as a consequence of its actions. And if this model is accurate, then the machine could use it to plan ahead. And it's a very classical thing to do in optimal control theory. There's a lot of roboticists here, and they say, well, yeah, of course we do this every day. But machine learning people really don't think of it this way, which is kind of weird. So inside of the intelligent agent, there needs to be some sort of world simulator, configurable world simulator. This is perhaps something that we have in our frontal cortex. And something that generates action proposals, something that predicts the long-term value of the objective that the machine is supposed to optimize. We know how to build the blue box and the red box. We have no idea how to build the green box. It's not that we have no idea. We have ideas. They just don't work very well. And the reason why they don't work. The problem with the world is that it's not entirely predictable. It's either stochastic or not fully observable or just very complicated. And so if I do a simple experiment, I want to train a machine to predict the future, and I show it segments of video of someone putting a pen on a table and letting it go. And then I ask the machine to predict what's going to happen next. The machine is probably going to learn very quickly that the pen is going to fall almost every time. But it can't really predict in which direction. We can't really predict in which direction the pen is going to fall. So what that means is that I can't train the machine to just predict a single value. Here is what happened, predict this. Because it's basically impossible to predict exactly. So there is a set of potential futures that is represented by this red ribbon here in the graph. And every time you run the experiment, one particular outcome is going to happen. But the machine may make a different prediction. And you don't want to punish the machine for making the wrong prediction as long as it's in the red ribbon of potential futures. The problem is that, of course, we don't know what this red ribbon is. It's determined by the data. And so what we might have to do is train a second neural net to tell us, or to tell the first neural net, you are on the red ribbon or you are outside of it. If you're outside of it, train yourself to produce something that's on the ribbon. And that's the idea which is called adversarial training. It's the basis of it, which I think is the best idea in machine learning in the last 10 years. And it's the idea that you train two neural nets against each other, or they help each other, really. So not totally against. It's more like a teacher or a critic, if you want, that trains a predictor. And I'm not going to go into the details of it, but basically the green box predicts, and the red box is trained to tell whether a prediction is good or not. And initially, it's not, it doesn't know how to tell the first network whether the prediction is good. But eventually, it learns to make the difference, and the generator that makes the prediction can use the discriminator to figure out how to change its output so that its prediction are good as far as the discriminator is concerned. And what's really cool about this is that the generator can have a source of random vectors, z, that will basically allow the system to produce different outputs for different values of the z, different predictions, if you want. So the first experiments were kind of astonishing a few years ago. This was a paper called DC GAN. One of the co-authors is at Facebook, so Ms. Chintala. And what you see here are pictures of bedrooms. The system has been trained to produce bedrooms from a bunch of random numbers. And those are non-existing bedrooms produced by the system. There's been a lot of progress over the last few years, a huge amount of work on those generative models, and a lot of hope that they can be used for all kinds of applications in content creation, in image generation. These are kind of early attempts at training them to produce dogs, and they produced Salvador Dali dogs. This work is a few years old. This is some work for video prediction. So what you see at the upper right, is what's produced by a video predictor trained on small segments of video using kind of a supervised learning, if you want. So basically, there's a least square cost that says produce the future, predict the future. And of course, because there are multiple futures, what the thing produces is an average of all the possible futures, which is a blurry image. If you train with those adversarial training techniques, you get much sharper images, which kind of makes sense. Some more recent work in this direction is for not predicting pixels directly, but predicting the mask of objects that can move around. So this is videos taken from a car, and it predicts that the car that starts turning left is going to keep turning left. The pedestrians that start crossing the street are going to keep crossing the street. It's very useful to be able to predict what's going to happen before it does happen. If you train a self-driving car, so that might be kind of a first hint that we might be using model-based systems, if you want, for autonomous machine learning systems. So I have a couple of predictions, and we'll end with this. One is that AI and machine learning is going to change the value we attribute to things. And this is me playing an economist here, and I'm not an economist, so take this with a grain of salt. Or ask Eric if I say something stupid. So you can today go on Amazon or whatever and buy a Blu-ray player for $47. And it's an incredibly complicated piece of technology, very sophisticated. It's essentially built by robots. And it's astonishing that you can build it for that price. If you want to buy a handmade ceramic bowl, the technology is 8,000 years old or so. That's going to cost you $750 or so. Maybe cheaper in some countries, but there is, real human intervention, real human experience, and we give value to this. And we're going to give more and more value to this, and less value to material goods that are built by robots, essentially. Similarly, with music, you can download Mozart's opera, Die Zauberflöte, for $7 or so. If you want to go to a performance of the Magic Flute, it's $200, $400, $800 if you want a really good seat. So the prediction is that there's a relatively bright future for creative and artistic professions that have kind of authentic human communication in them, and creation and emotion communication. We can build machines that will do jazz improvisation, but they're not going to communicate human emotions. They might fake it pretty well. So as I said before, AI is a general purpose technology, according to many economists, and it will affect many sectors of the economy, but it will take a long time before it kind of diffuses in all sectors of the economy. 10 to 20 years is what economists say a technology takes to go everywhere and improve productivity. And so automation, of course, leads to job displacement. This is not a new phenomenon. I don't think AI is qualitatively different from previous technological revolutions in that respect. That creates technological unemployment, which means people who don't have the skills that are required for this. So I kind of drew this thing where you have the set of skills that are required for the economy, and then the set of skills that people actually have. And as technology moves, there is a bunch of people kind of left behind. And I was really worried about this because I was thinking that as technology progresses faster and faster, there's going to be more and more people left behind. But what economists are saying, what I learned recently, is that in fact it's the fact that there are people trailing behind that limits the speed at which the technology disseminates in the economy. So there is a limit to how many unemployed people you can have. It will limit how fast technology progresses. So I think to end, I think we'll have true AI when we solve this problem of getting machines to learn the way humans and animals do, this predictive learning, which we're working on very actively. A lot of people also at DeepMind and various other labs work on this. Discovering the basic principles behind this may take 2, 5, 10, 20 years, we don't know. Once we've discovered those principles, it might take another 10, 20 years to actually figure out how to reduce it to practice and make it work effectively. That's always what it takes. Convolutional nets were, first produced in 1988, and it took about 20 years for them to be kind of pervasive. And there is a danger that perhaps intelligence is not that simple. It's a kludge, and it's going to take much longer to produce intelligent machines. So I'm going to end this here, and thank you very much for your attention.